Okay, so in this video, we want to talk a bit more about how to deform or move volumes, with VEX. Now, the first thing before we start actually warping volumes is to understand how we move voxels in a volume. Because at first, it's a bit hard to understand how this works. So what we have here is, a grid or a field or a volume, call it whatever you want. Those are a couple of voxels. And in it is some kind of cloud or something. Doesn't really matter. And as you know, those voxels, let's say, have a value of 1 and the rest have a value of 0. And as you can see, each voxel has a number so that we know what voxel we're talking about. Now, if we wanted to move this cloud, of course, what we can do is we just move the whole volume. Sure, that's always possible. You can take the whole volume, translate it, rotate it, or scale it. But what we want to talk about is how to move voxels inside a volume. So it's more about this here. And this is important to understand because when we want to do more complex stuff like actually deforming a volume, we can't just take the whole volume. What we actually have to change is the contents of the voxels. And this is important. When you look again at what's happening here is, and this is why I gave each voxel a number, the voxels themselves are not changing. And this is what it's a bit confusing about volumes. You cannot take a voxel and move it around. That's not how it works. The voxels actually, relative to a volume, cannot change in position. They always have a certain position. The only thing you can change is the content. And this is exactly how we move a volume. Because what we do here basically is we take the content of voxel 26 and put it into the voxel 27. So it looks like this. And when you do this with the content of each voxel, then it looks like the whole cloud is moving. Now, the good news is we don't have to actually know the number of the voxel. We actually can work with positions. So basically the density of voxel 28, if we wanted to move it to the right, is supposed to get the value of any kind of data in a certain distance from my current position. So the logic is the density of voxel 28 in the next step will be the density at the current position minus some kind of distance, let's call it x. And this is a bit confusing for beginners, but this is basically the logic. If you do that for every voxel, then it seems like you move the volume in space, but all you do really is you're reading out the content of a neighbor voxel and replace the current voxel with that value. So the logic here is how it is set at the bottom. You actually sample the volume of a certain position that is relative to your current position. So we read out from the current volume the volume density to then write it back into the density of the current voxel. And what we read out is not the current position, but the current position with a certain offset. For example, we move it to the left or to the right. And this will then give you the impression that the volume is moving, even though the voxels are not actually changing. It's just the content of each voxel that is basically moving to the right. So let's have a look at how this works in Houdini. So when we look at this volume here, which I created with a cloud and a cloud noise node, we can, of course, when we press Shift W, see the box that it lives in, or the volume. And of course, with a transform, we can, transform the whole thing around, and we can rotate it and we can scale it. There you go. But this is not what we want. We want to deform it, and then this is not enough. If you imagine how this would look like in form of voxels, of course, technically, it would look like this because the resolution obviously is very high, but then you wouldn't see anything. So I chose this low res to understand it better. What we want to do is we want to move the voxel content inside of the volume without moving the volume. And we can do this, very important, with a volume wrangle again. And we want to offset the content. And what we want to write here is the density, of course, for each voxel. And we want to read out basically the content of the neighbor. And for, the volume sample, as we know, takes 3 inputs. The input number, or the volume we want to read from, which is the first input, then the name of that volume, which of course is density, because we want to read from ourselves. And in the simplest form, we just take the current position, and what would happen here is nothing, because we basically just read out the value from ourselves, from the position that we're currently at. And the trick here is now to just add to this a little offset. And we can do this, for example, with a vector parameter. So let's call this offset. And let's make this a bit bigger to see it better. There you go. So currently still nothing is happening because that offset is 0. But as soon as I change the number here, you can see what's happening. Wait, this is X, so maybe like this. We basically move the volume from left to right because we're reading out the voxel from left to right. And of course, this is a vector, we can do this in all directions. But of course, what you can see is we are limited to the area that our volume covers. And also there's something strange. When we move it down, you can see there's something missing at the bottom. You would think that the whole volume is moving. The reason why this is happening is that we're currently using a VDB here. And I did this on purpose to show you that when we look at the VDB tree, for example, VDB visualized tree, the thing about VDBs is that they only have certain voxels that are activated, and we can't fill a voxel that is deactivated. The trick here is either to activate each voxel, or what I often do is I just take a convert VDB and convert my VDB into a normal volume. And then, as you can see, the result is different because now you can see each voxel can actually be written. So we will get a proper movement and there's nothing, cut off. Same for Y. So be careful with this technique. Always make sure that all the voxels are activated. Otherwise, it might look like this, that you can only basically move your volume wherever there was a volume before. And of course, this technique also works for any other type of volume. So for example, a velocity field. So here I have a velocity field that looks like this. And basically this is the voxel grid, if you want to imagine it. And we can do the exact same. The only difference here is, and this is why I wanted to show this to you. Of course, this time we don't have a float. We have a vector that we want to change, the velocity field. And therefore the name of the volume is different, of course. And very important, if you want to change a vector volume, then you need to use the volume sample V, as we learned in the other video. But besides that, the technique is the same. So I can as well move now my velocity field inside of my volume in any direction. So this might be a way for you to change your velocity fields as well, not just Fock volumes or SDFs maybe. Now, why is this cool? Instead of moving each voxel in the same direction with a vector, for example, we can move each voxel in a different way. For example, we could move it by a noise instead, like here. So we replace the vector with a noise, and then here we have a noise strength. And then you can see we can basically deform the voxel. Now this looks pretty ugly because we have to consider a couple of things, like making sure that the noise is added and subtracted so it moves in both directions. But here you can see the idea behind it. Artificially, in this way, you can warp or deform your volume and add more detail to it that wasn't there before. This is pretty much the same that the cloud noise is doing as well anyway. It uses a noise to offset the values of the original volume and basically moves the values away by that noise. And we can do this ourselves with this technique of reading in the value of another voxel based on the current position and some kind of noise that is different for each voxel. And the result will be some kind of deformation because every voxel is moving in a different direction basically. Now, since this is noise-based, mostly we do this with VOPs actually because the result is simply much nicer, but this is the core idea. And in this video, I just wanted to make sure that we understand this concept. So I hope this is helpful. So thanks very much and see you later. Cheers.